I'm just hitting the record button now, so I don't forget to do so in a bit. Okay. So let's go ahead.
Like a jean shirt.
All right.
It's not.
Okay, so a couple things first. You got an email for a post-survey participation. I would really appreciate it if you had the chance to fill out this survey at some point. I'll send you another reminder, but it really does help. But this is part of a research project that I'm involved with. I don't see your responses; they're all anonymized, but I just provide. But it would very much help us with the data collection if you're able to respond with this. So I would consider it a personal, I would be personally grateful if you did this, participate in the survey. It really does help with our data collection and the research project that I'm working on this. So also, likewise, please fill out your student feedback forms. I read them all. I read all those comments. And I do use them to make modifications to my classes to do that. They also do get looked at when as part of when I'm like applying for promotions and things like that. So just keep it, so they can. The point being is that you aren't just screaming into the void when you leave a comment. Okay, can a bulwark of positive comments or negative comments do basically show like a very specific thing about professors teaching that does get looked at by the chairs and the administration. So these things have an impact. But if you have valid criticisms that you don't feel comfortable telling me about in my, to my face, that this is a perfectly good place to put it. It's all going to be anonymous. I believe there's also a specific form you have for your TA. So if you have criticisms about your TA or things to say about your TA or kudos to give to your TAs, there's room for that as well. But please, the student feedback forms, computer science typically has a very low response rate, and I'd really love it if we could help get that up. It really does help, even if you don't leave any comments, or if your comments is K was great or K I didn't like it. Just getting comments in does matter to us. Okay, so survey SSFs. I know you're being asked to complete a lot of things, but these do have an impact on students beyond you. So I have sent out an announcement that you should have gotten an email where I've just sent out a bunch of materials, including this kind of checklist of all the stuff that we've gone over. Data structures isn't a rapidly changing topic, therefore this PDF hasn't really changed since 2017, but that's okay. Big O, it's just not in the same order, right? Concepts you'll want to make sure you know: big O notation, recursion, sorting. Specifically with sorting, you want to know your insertion sort, your quick sort, and your the quick sort with regards to the partition algorithm. So not the whole abstract quick sort takes everything takes everything less than pivot, puts it on the left, takes everything greater, put it on the right. We want to know precisely how it does that in place. Merge sort, why we care about merge sort, because it's consistent. It always is n log n. Huffman encoding, I don't believe that's going to be on the final exam, but it's worth remembering. For the exam, you will not write any data structures, but you'll want to know how to write code that uses them, right? Know your lists, your array list, linked list, your big O's, your notations, your stacks, your queues, your trees. What's the difference between a tree, a binary tree, and a binary search tree? And then our algorithms are either find based or traversal based. Find based meaning that we're going to be, and find based algorithms are log n time and traversal are O of n. Find means we're basically looking for a specific node in the graph, in our tree, right? And we're just simply cutting off and we're basically eliminating a large swath of the search space every time we go down an edge, versus traversal, meaning that we're iterating over the entire thing. Okay. Heaps, hash tables and and specifically the things we build with them. I've had hash code I will probably do some kind of hash code relay problem on the final exam. It's just, or not hash code, but hash table, either hash set or hash map. Just know how your collisions are resolved with these. I wouldn't put these down here if they weren't important. And for graphs, you want to know the two ways to represent a graph: adjacency list, adjacency matrix, and then your traversal and path algorithms. In other words, breadth first search, depth first search, and Dijkstra's algorithm. All right, so that's good. I think I've done my job. So see you, everybody. Kidding. Now we want to do some actual final review. So first I went, rather than going and writing my own, because while things are taught in different orders in data structures, a lot of the end result for most classes is the same for a lot of classes. And even though there's some overlap between we have computer science. We basically teach, CS 1, 2, 3, 4. We have programming, object-oriented programming, data structures, and then algorithms. And depending on the specifics of how and when you receive your degree, when you're going through your computer science IST program or data science program, what university you're going, how that information is spread out really depends on the specifics of the particular curriculum that was developed. So for instance, in this exam, there's a lot more about big O notations that you would we normally go put in algorithms and in 10-15 and in our math concepts classes. But at the same time, there's still some very good data structure related questions in here. So you should be able to identify the things that are relevant for the exam fairly straightforward in some of these. For instance, let's go ahead and go for the one that's the shortest or has the least content, which is the 2017 entrance exam to the Graduate School of Information Science Technology to the University of Tokyo. That's kind of the best university in Japan. So this is their entrance exam to the graduate school. It consists of 4 problems. The first problem is a math problem involving something they define as the P norm, which they have these function things and they ask you to prove. So it's more of a math kind of thing. It doesn't matter. That's not what we're here for. Second, for a non-deterministic finite automata M over alphabet sigma, write the language of M is a subset of the alphabet for a set of words accepted by M. And then it's got a flow chart about these things. This is all about automata theory, which is basically saying it's flow charts. Everything over here can pretty much be, non-deterministic finite automata has equivalence as deterministic finite automata, which has a equivalence with regular languages. So it's kind of interesting in these senses, but I mean, again, not what we really care about for here. Problem 3, consider the problem of sorting an array of integers using the heap sort algorithm. Okay, now we're on familiar ground, okay? Question 4 was about circuits, because again, and that's all 4 problems. Again, it's a matter of what do they care about. Every university has a different kind of idea here, but there's a lot more math. So let's go ahead and look at these sub-problems for problem 3, because these are the kind of questions that even if we don't go over heap sort, they're useful for knowing about, kind of equivalents for quick sort and merge sort. So heap sort consists of 2 phases. Explain what's performed on each phase. What are the 2 phases of heap sort? Right? So given an array and we want to do heap sort on it, what are the 2 phases? Yes.
Yeah, I think it's like a max.
You have to heapify it.
Yeah.
You have to turn it into a max heap. And then you have to sort it. Right? So it's the heapify and then the sorting. Considering this, consider sorting of the following array using heap sort. Draw the tree structure of the heap after the first phase. In other words, after we turn it into a heap. All right, so for reference, okay, so we can go ahead and zoom in and just give ourselves a nice big swath of space. Okay. So when we do heap sort, right, it's considered an array, but that array is a complete tree, and so we can list the items left to right like this. 3, give me a second, let me go, since we're on white, let's go back to red. 3, 8, 1, 5, 4, 9, 7, right? This is index 0, index 1, 2, 3, 4, 5, 6. Okay, let me get rid of that so it's not so cluttered, but that's the point. Okay, now to turn this into a heap, to heapify it, there's 2 ways to do this. The incorrect way, but the kind of way you would normally think about it, which is you start with item 3 and add that to a heap, then add item 8 to the heap, then add item 1 to the heap, and so on and so forth. Well, we've already got that in an array. So basically, if we add 3, add 8, add 1, add 5, add 4, add 7, and add 9 and add 7, that's basically working from the top down. A more efficient way to do heapify is to work from the bottom up and basically push down on each item to see in this heap to see if it can if it can be pushed down into a lower level. So the way that works is that we look at 7, we start at 7 and we go in reverse. 7, can't push that down as a bedrock. Same with 9, 4, and 5. So part of the reason we do this is because we get the bottom layer all done for free automatically. Okay. Now, can we push 1 down any further? No, we can't push 1 down. Well, actually, we're supposed to turn it into what? A max heap? Supposed to turn it into a max heap, yeah? For heap sort, yes? Yep. So in that case, we do need to push it down. So we need to swap it with, so the highest item rises. We swap it with 9, 1. Okay. That's done there. And now we need to push, 8 down. Can't push down 8 because it's higher. Sorry, it's a higher priority, so it wants to stay at the top. So we keep that there. And now we push down 3. 3 is smaller than both of its children, so we need to bring one of the bigger children to the top. Specifically, we're going to bring the biggest children to the top. So what we'll do is that we'll swap 9 and 3. And then we got to do the same thing over here. We got to continue pushing down. 3 is not smaller than 1, but it is smaller than 7. So we're going to swap 7 and 3. Okay, and there we go. That's what it looks like after the first phase. Okay. What is the time complexity of each phase when sorting an array of length n? Explain the reason. Okay. And then we're gonna kind of leave it from there because the other questions get on, which are a bit more interesting, but they aren't really relevant for it. I'll skip question 4. Question 5 we'll get into, but let's see. Time complexity for each phase. Time complexity for each phase is as follows. O of n for the heapify plus, and then for the heap sort phase, actually, so O of n plus for the sort phase n log n. All right. So why is this? So to heapify it, Wikipedia has a fairly good write-up of this, but basically as we push down each of these arrays, we've kind of as we push down on each of these items in a complete tree, we basically do one operation here, one operation here, one operation here, one operation here. Then at most 2 operations here, 2 operations here. And then 3 operations here at most. As opposed to adding it the other way, which would be, if we did the other way, which takes n log n, it would take 1, 2, 2, 3, 3, 3, 3. So going this way ends up being cheaper, and we actually do a bit of math. It will which we don't really care about for this class. It turns out to be O of n time as opposed to n log n for heapifying. Turning something into because honestly, we're just looking at each item, and on average, we're just moving each item once. Okay. And then for the sorting process, what we do is that we take when we're sorting when we're doing heap sort. Okay. What we do is we take this item and we delete it and replace it with the last item, which I'll call L. Okay. We do our normal operation, which we would for in Quicksort, but this item that gets deleted, we don't actually delete it. We move it to the location where L was, and we just kind of have it hang out there. But long story short, then figuring out where L needs to go now, since we just moved it from where it was in a valid heap to the top of the heap, so now the heap's all invalidated. Revalidating the heap takes O of n time. And sorry, it takes log n time. So we have so it takes log n time because there's log n layers, and we have to do that O of n times. So n times log n. So it takes n log n to resort that. Answer the time complexity of obtaining a sorted list of the smallest k elements from an array of n using heap sort. Explain the reason. This is actually a very popular use case of heap sort, which is that you can sort just a subsection of it, of the array. If we did min heap instead, if we sorted it to a min. So with the way we typically do max heap, right? Okay. So let's think about this for a second. Normally we transform this thing into a max heap, and then as we go, we've got basically the biggest items over. We have basically the biggest item, which I'll call Z, and then over here we'll go the next biggest item, which we'll call Y, and then X, right? We get the biggest items in each of those locations. And basically we figure out what the biggest item is, then the second biggest item, and the third biggest, and so on and so forth. If we flip around how we do this, build a min heap rather than a max heap, we'll get the smallest item there, then the second smallest, and the third smallest. So the amount of time it would take to get a sorted list of k smallest elements would be, well, we want to do heapify, which would take O of n plus, and just spitballing over here, there's probably a more efficient way, but it would take, fixing each of those takes log n time, but we'd only do k of them so that ends up being pretty short, which ties into the other thing, which is the execution time of heap sort on modern computer systems is often longer than some other sort algorithms, such as quicksort and merge sort when sorting a large array. Well, explain a possible reason why that might be the case. And the reason is actually fairly obvious, which is that when you think about it, normally we get rid of this, but when we're comparing things that are of that, quicksort has n log n time, merge sort has n log n time, but we have this cost here of the heapify that we have to add in. That's a possible reason for heap sort taking longer, because we have to heapify. And when it's large, this is large. And there's not too much of a huge difference between these things as compared to O of n squared. It's still a big difference, but not like a huge difference. Like if you're, again, just to kind of be clear, this is if n is equal to 2 to 32, so that's like a 4 billion or so, okay? then the runtime would be approximately around this size of, you know, some equation that deals with 2 to the 32 power plus 2 to 32 power. And then this is log n, so this is roughly around 32. You know, because logarithms get rid of those. You know, would be log base 2. So, you know, this grows fairly quickly. And you know, so anyway, long story short, this bit matters in comparison to the other ones, but we still use it because of the fourth case over here, which is that you can get like the smallest items out of it fairly quickly. Okay. Anyway, if anybody has any corrections to make on that, you're more than welcome to. If you know I got anything wrong, I don't think I did, but regardless. All right. So now I'm going to look at this Harvard practice final exam, which I'm a big fan of. So we'll go through each of the questions in turn. And I like this because it touches on some of the later semester material a bit better than other stuff. So suppose that A, B, C, D, and E are pushed in that order onto an initially empty stack. Okay, A, B, C, D, and E. And I just stack them onto. I like to do my stacks vertical and my queues horizontal. That's just me. Okay, it just makes sense to me that way. Okay, then S is popped 4 times. Each time as it's popped off, it's inserted into an initially empty queue. So E gets popped off, puts into here. D gets popped off into here. The queue goes this way, left to right. You know, so this is the front of the queue over here. Always like to draw these things rather than try to work it out in my head. C, B, so it's inserted. So as each item is popped off, it is inserted into an initially empty queue. Great. If 2 items are then removed from the queue, okay, we remove from the front, 1, 2. What is the next item that would be removed from the queue? There's C. All right, fairly straightforward there. Okay. If the binary tree below is printed in a pre-order traversal, what would the result be? Okay. So first off, pre-order means we handle, if we start here, we'll handle ourselves, then we'll do the left subtree, and then we'll do the right subtree. So first off, anything with A and B are incorrect because they start with 9 as opposed to 6. So we can just simply do our pre-order traversal. It would be 6, then go into my left subtree, which would be 17. Then we go into that left subtree, which would be 9. And there's only one of those that fits. But the pre-order traversal would be, you know, we do 6 first, then we go into the 17, then we go to 9. So we're done with 17th left tree, so we go into 17th right tree. That's 4. We're done with 6 left subtree, so we go into the right subtree. 2. Go into 22's left subtree, which is 16. We're done with 22's left subtree, so we go into 22's right subtree, 12. Okay, now we get into a good question for newer materials. A graph implementation that uses a 2-dimensional array to represent edges would be most reasonable for which of the following cases? So remember, we have 2 ways of implementing a graph as a data structure. We have the adjacency list and the adjacency matrix. Adjacency list says, hey, in some way, either with a map or a list, it says, here is my node, and here's the list of all the nodes that I'm connected to. You know, all the nodes I have an edge between, and maybe some of the information I have, or it might be a list of the edges and their weights and this stuff like that. But it's just it can be fairly sparse. On the other way, a 2-dimensional array basically says, like, here's A, here's B, here's C, here's D, right? And so on and so forth. And I'll fill it out with the edge cost in between them, you know. And maybe I'll use infinity to represent that there's not an edge between us. Okay. So which of the following in which of the following graphs would we want to use a adjacency matrix versus an adjacency list? A graph with 1,000 node and 1,200 edges, a graph with 100 nodes and 4,000 edges, 1,000 nodes, 10,000 edges, 10 nodes and 20 edges. I haven't seen this problem in like a year because I wasn't able to find this exact thing last year, I think. None, since a graph can only be represented by a linked structure. Oh, well, we know that that one's incorrect. So, okay. So the question here is basically, well, when do we use a adjacency list versus an adjacency matrix? And the question is whether it's a sparse or a dense graph. We'd like to use adjacency lists for sparse graphs and adjacency matrices for dense graphs, because for a dense graph, that in a sparse graph, this notation would have a lot of wasted space in it, but the lookup time is fairly good. Whereas in a sparse graph, the list notation makes sense. Okay, how do I know if it's a sparse or dense graph? Well, long story short, our textbook defined it as 25% usage. What does that mean? 25% of all possible, if 25% of all possible edges exist in a graph, then that's a dense graph. Okay, so in other words, there are, do you want me to use V or N for nodes or vertices? Doesn't matter. We use vertices typically for this. So for instance, the number of vertices, let this represent the number of vertices, okay? The number of possible edges you can have in a simple graph is V squared, because you have V nodes and each of those nodes can connect to the other ones, right? So that's the maximum possible number of edges. So basically what we're looking for is if the number of edges divided by V squared is greater than or equal to 0.25, or whichever one is the max, So for instance, let's test this out. If we have 1,000 nodes, then how many possible edges are there? And yes, for the sake of simplicity, we are assuming that nodes can have edges that go to themselves. They can have edges that look like this, which is a thing you can have. But for 1,000 edges, 1,000 nodes would give us, that's 1 million possible edges that could exist, right? Which is, so now if we have 1,200 edges, I have 1,000 nodes, well, doing some quick and dirty math, that's 12 out of 10,000, 12 10,000ths, which is not 25. We can just stop there. That's not 25%. Okay. Okay, let's go on to the next one. 100 nodes squared would be 10,000 possible edges, 4,000, and we've used 4,000. So we have 10,000 possible edges because this was 100 times 100 down here. 4,000 edges have been used. Let's get rid of the zeros. So we have 4 out of 10, which is 40%. So this seems like so B seems like our best choice so far. It's probably the correct answer. C gives us a similar situation where we have 10,000 edges out of 1 million. So we have 1% usage there. And 10 nodes and 20 edges is actually fairly close. 10 nodes would give us 100 possible edges. And 20, which is about 20, which is quite literally 20%. So our answer is B, because 40% of the node possible, this is dense because out of the 10,000 possible edges, 4,000 of them exist. Everybody, that makes sense to everybody? Just a matter of figuring out which one of the, which is the ones that's sparse. I like this one. It was a very good problem, I thought. All right, so, they go into different things, but one thing they didn't go into was generics. So they just use ints. That's fine. A binary tree is constructed of nodes that have the following class. they have a value, a left and a right. We have a mystery method over here that we're supposed to consider it. And I consider it to be, okay, I've considered it. Anyway, node, it's just such an interesting choice of words, consider it. Node root. All right, it returns a node. And if I don't have a right subtree, so if I don't have a right subtree, I'll return myself. Okay, that's what it says. Not this dot root, but this is the root. Remember, root here is the root of a tree or subtree. So if I don't have a right subtree, I return myself. Otherwise, I return the result of calling mystery on my right subtree. In other words, I think, so now I'll actually consider it, which is that I go through, and basically what I'll do is that I'll just, if I call it on the root of this dot root of a tree, it will travel all the way to down to the right and grab the rightmost node out of a tree. Okay? Rightmost node out of a tree. Now, is this a binary tree, binary search tree? Binary tree. Okay. So we can sort through, it's one of those, right? The ones where you have to say which of the three is true, which combination of the three is true. Don't you love those? You consult three supposedly tech-savvy consultants, and you get the following three opinions about what the method does when passed a reference to the root of a node of a binary tree. Consultant one says it returns the last node of an in-order traversal. Consultant two says it returns the last node visited by a post-order traversal. And consultant three says it returns the last node visited by a level order traversal. Which of these three opinions is correct regardless of the content? So level order traversal, again, that's just a fancy way of saying breadth first search. It's just breadth first search over a tree. The only reason we don't go over it in the tree chapter is because I can now just say level order traversal is breadth first search. You've done it with graphs. And you don't do it recursively, Okay. Or you really don't want to. Anyway, which of these opinions is correct regardless of the contents of the tree? All right, so again, what this does is that this gets the rightmost node, okay? So 2 is incorrect. Okay, just straight up incorrect. That's only true if your tree is shaped like this. And you've got no rights, so your root node has no right subtree, because then you'll return the top node of the tree, and in a post-order traversal, the topmost tree is, the root is always done last. Okay. Now 1, on the other hand, that's got to be correct all the time, because the rightmost node in a binary search tree is the largest node, right? And when we're traversing through it, that means in in-order traversal, we'll always get the rightmost node, because what we do is that in a binary search tree, we handle my left subtree, okay? Then we handle myself, and then I handle my right subtree. Eventually, you're going to get to the rightmost node and the rightmost node has no subtree, so it's going to handle its last subtree if it exists, then it's going to handle itself. So it's going to be the very last thing, right? The rightmost node is always the biggest node. In-order traversal always returns the biggest thing. Level order traversal, number 3, is a bit trickier because it looks like it will work almost all the time, right? Especially if you always draw a complete tree, right? You'd think, okay, that's the rightmost node, except wait a second, level order traversal will return this guy last. If you always try on perfect trees, you'll get not all, so you always want to, so the main thing you need to do is that you got to do science in these things. Specifically, you got to do the falsification part of it, which is that you've got these hypotheses that have been postulated. And the job of science, when you have science's job when you see hypothesis, is that you don't try to prove it, you try to prove it incorrect. Science is all about doing that falsification part, making a hypothesis and then throwing every single reason you can possibly throw at it to see if it's wrong. Doing so, if your hypothesis survives, it's stronger. Maybe you can actually consider that you've got a good hypothesis here. Okay. So A, one only. With this poorly chosen hash function, it's possible to have a situation in which the search time of a hash table of n items goes to. So let's consider doing linear. Let's go ahead, for the sake of argument, consider linear probing as our resolution, right? If my space is taken, then look at the next available space. So what is a very poorly, so let's go ahead and write a very poorly chosen hash function. H of k, given a key, I'm gonna go and put the item, I'm gonna say that it goes at index 0. Doesn't matter what the key is, I'm gonna go and put it at index 0. So the first item goes in immediately, the second item you put in gets collision and goes 1 over. Second item has to go 2 over, the third item we put in goes 2 over, third item goes 4 over. So in other words, as we add when we add the nth item, it goes into index n, n minus 1, and that takes all of n time. Right, a poorly chosen hash function takes that long. I think you'd have to have a very poorly chosen resolution, a conflict resolution, to get any of those times. Yes.
Can you explain what they mean by poorly chosen?
Okay, so hash functions, a well-chosen hash function will distribute given the entire universe of keys, okay, that hash function is trying to basically take all those keys and distribute it into some limited number of indices as uniformly at random as possible. Essentially, I'm trying to take these items and put them into, you're trying to distribute them as best as possible, okay? And as evenly as possible, much like a uniform random distribution. Except we're not completely random here because, given an input, you always get the same output. But the point being here is that we're trying to distribute the things evenly so that we don't get too many collisions, right? You're going to minimize the number of collisions if everything's distributed evenly. And a poorly chosen one would basically say, was what I did, which is simply said, let's just put everything in the same place, which is going to cause collisions. So poorly chosen hash function has lots of collisions. A well-chosen one has very few. Notes for doubly linked lists are to find out the following structure. Hey, you should recognize this from our own practice exam. You have previous and next. Which of the following of the expression does not refer to the third node in the list? So we've got two nodes here. We've got N and we've got P, and they're both doubly linked, nodes in a doubly linked list. P.next is this guy. N.next is the third one. P.previous.next is P, so there's our answer. P.next, previous.next, that's 3. And N.next, previous.next, that's also the third one. So C is our answer here. It's the one that doesn't refer to the third node in the list. Okay. That's an unimportant one. I like this. Now this one is an important one, I think, because it is definitely one I like. Yes. 5, this one?
Yes.
So the idea here is with a poorly chosen hash function, you get lots of collisions. Collisions take a while to resolve. The more collisions you have, the longer it takes to resolve. With a well-chosen hash function, you take basically everything, you get with a well-chosen hash function, you get this constant runtime essentially. Okay. Poorly chosen hash function. Well, I went argumentum ad absurdum, which is basically I said, let's make this as absurd as possible. Let's choose as bad a hash function as possible. Okay. Okay. So what I did is I chose a hash function. I created a hash function and said, here's a poorly chosen hash function. Everything goes into index 0. let's stop thinking about linear probing and instead do collision resolution with chaining, where basically everything that goes into the same index goes into a linked list. So so if I use this as my hash function, a very poorly chosen one, then every single one would go into the linked list at index 0. And thus the search time for that, well, to find it, I'd just be searching the linked list with extra steps, which would take O of n time. Because there'll be n items in a single linked list. Yes.
You were trying to add like n items. Wouldn't it be like every time you add an item, you search an additional distance? So like for the first item, you have to search 1, and then for the second item, you search 2. Wouldn't that be actually like a 1 plus 2 plus 3 something?
Well, it says for a search time for a hash table. I think we're having a difference of interpretation here, because I'm not talking about the adding time. Yes, it would take, if we were adding n items in linear probing, it would take O of n squared time. In chaining, it would take O of n to add n items, because we're just simply adding onto the end of a linked list. It takes constant time there. But again, that these are for in these poorly constrained things. But I believe the question is asking for search time in a hash table with n items. In other words, finding a single item, which would be O of n. So yes, your analysis would be correct in that in the conditions you had set up first. All right, so so let's take a look at this again, because we're going to be talking about hash tables even more in this question. Okay. So a police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so it can be determined very quickly whether or not a given license plate is in the database. Speed of response is very important. Efficient use of memory is also important, but not as important as speed of response. Which of the following data structure would be the most appropriate for this task? In other words, we want to basically, so what is this asking? It's saying, which of these, if I'm going to use it with the contains method, right? That's what we're doing. Does this exist? We're just trying to see, does this exist in my list or set or array, right? Which of these is the best? It says we want the fastest one possible, but if I need to break ties, memory is going to break the ties. Make sense? So a sorted linked list. And I like this one because we start out with a sorted linked list. Not a sorted array, a sorted linked list. A sorted linked list, the amount of time it takes to find something in a sorted linked list is, well, it's O of n, because honestly, your best way of navigating through a sorted linked list is to start at the beginning and check the next item, and then check the next item, and then check the next item, because you don't have a pointer to the middle of the list, and then you don't have a pointer to the midway point. You can't perform binary search on this one. So sorted linked list, O of n time. Okay. And in terms of memory, it takes about O of n overhead, right, with the nodes and all the containers, as compared to a sorted array, which has like no overhead, right? Just no overhead whatsoever in terms of memory. And how quickly can we do it? Well, I just alluded to binary search. In the sorted array, you can look in the middle. If you found it, great. Otherwise, look at the appropriate midway point in the smaller half or the bigger half, right? Or the half of the smaller items, I should say, and the half of the bigger items, because those halves are going to be evenly sized. And that takes O of log n time, okay? So if we cared about memory, we really couldn't do better than a sorted array, because there's just no extra overhead on a sorted array, okay? Now, open addressing with 1,800 entries, 3,600 entries, or 10,000 entries. So, what we need to know here is, and I'm going to look it up. Knuth, hash table, search, average collision formula. Let's see. So we know, so Knuth has this idea for average collision. Sorry, average collisions. Open addressing. There's a formula that I've got to look up that I know that I think I know it off the top of my head, but I don't want to really embarrass myself by not saying it, by not doing it right. I have it in the slides. I know. Linear probing. Analysis. No. There it is. Load factor. Okay. So the expected time for a successful search, in other words, looking for a item that exists in this, is 1 plus 1 over alpha. Let me go ahead and rephrase that. So for hash tables, what matters for the speed of everything is what matters for the speed for a hash table is the load factor, which we'll call L. Okay. Rather than using, alpha because that's Greek. Why bother using L as our load factor? What is the load factor? That's the percentage of slots that have been taken up. Again, going to our garage, the parking garage analogy that I'm so fond of. We're looking at a parking garage that's completely full, half full, or almost completely empty, right? Now, the interesting thing, because we're looking at the load factor, only looking at the load factor, the analysis of our algorithm doesn't have n in it. So the amount of time it takes, the expected amount of time, is 1 plus 1 over 1, minus the load factor, okay? And the load factor is basically, what percentage we're filled up. 1800B would be fully filled up, which would be 1 minus 1, which would give us dividing by 0. So let's not do that. Instead, we'll just, we'll change the parameter of the problem to be close enough for us to use, which is, I'll say, what if it was, 1620 entry, sorry, open addressing with about 10% more. Let's say, what if it was 90%, if our load factor was 90%? That's close enough and easy enough for us to do our math, okay? So in that case, we would replace the L in this case with 0.9. 1 minus 0.9 is 0.1, which is 1 over 10, right? And 1 divided by 1 over 10 turns this entire thing into 10, so it'd be around 11. And instead of using instead of using this, we'll use basically, it will say expected lookup is equal to that rather than go, because it's all constant. So expected lookup is equal to 1 over 1 plus 1 over 1 minus lookup factor. In this case, this entire thing became 10 at 0.9. So it takes a lot of steps. In other words, we would expect, if it was 90% full, we'd expect after 10, expect to check about 10 spaces, or sorry, 11 places. Makes sense though, if if your parking deck is 90% of the way full, you're gonna have to check like a bunch of spaces. Okay. Next, what if it's got 3,600 entries? In that case, that's about what we like to keep it at, about half full, half capacity. I mean, like our parking decker analogy here holds. If your parking deck is half full, not gonna take too long. 0.5, half full. This becomes 1 minus 0.5 becomes 1/2. 1 over 1/2 becomes 2. Just some algebra that I've had to memorize and reflexively do, forever. So 1 plus 2 is equal to 3. So this is 11, 11 expected step, 3 expected steps. And then with 10,000 entries, well, again, let's go ahead and simplify the math. Let's assume that instead of using 1,800 things, 1,800 possible entries, we'll do a maximum of 2,000, which means our maximum load factor is about 20%, right? So 1 minus 0.2. Again, I'm just simplifying the math because it's going to be close enough for us to make our analysis and our judgment. 1 minus 0.2, which is going to be 0. Hold on a second. 1/2 full. Let's see, did I do it right? Thought I did. Is okay. 1 minus. Okay. So 20% of the way full would be 0.8. Sorry, it would be 0. Oh yeah, I did it right. Okay, my bad. I was mentally missing a step. So this would be so this 2 becomes 0.8, which becomes 4/5, which becomes 5/4, which becomes 9/4. I have no idea why I just blanked on that basic math. But again, the more you work in like the letter-based mathematics, the worse you get at the number-based mathematics. It's just so that's like 2 versus our bit more than 2 versus our 3. So we had 11 steps versus 3 expected steps versus 9/4, which honestly we'll just call 2. Okay, for just close measure. Okay, so they're all constant time. They all have over time. The question is, but mind you, this one's going to be very poor runtime because you're getting collisions left and right. 11 steps versus, that's going to be longer than the log n over here, right? If you've got 1,800, let's see. So, that's going to be much less. Sorry, that's, 2 to the 11th is going to be a much less value, I think. So, whatever. Point is that we're not going to use this one. We're not going to use this one. And the half table with 2 or 3 steps is going to be better. So which one do we want to choose? Well, I think this one comes up to the professor, but honestly, they're both constant time. And this is way more memory efficient because this one, it's like having a parking deck that you have to pay massive property taxes on because you're using up all that space. But you're not actually getting use from that space. It's all just a bunch of blank and wasted memory sitting there. With the hash table over here, you're only wasting a little bit of memory. The answer is D. Again, this one I like because it involved us having to look at something we don't normally look at. A Huffman tree is constructed for a text document containing 5 characters. I assume it means 5 types of characters as opposed to only being 5 characters long, because that would not be a very exciting Huffman tree. The character E appears the most frequently, followed by the character I, having the next highest frequently. Which of the following could be a Huffman tree for the document? So 1, it's got 1, 2, 3. 1 is immediately out of the gate because Huffman trees, right? They don't have internal nodes with data in them. The internal nodes only have weights. Only the leaves should have should have the letters. 2. Okay. E is the most frequent character, so it has the least steps over here, and then it says I is the second most frequent character. Yeah, this checks, especially since since we would have maybe done these things first. I can see this tree occurring. And then we have this tree. And I and E have the longest values. So 3 is wrong because those would mean that it has the most, that these have that these characters appear the least amount of times. So I would say it's only 2. unless you can prove to me that there's some way that 2 doesn't isn't a valid Huffman tree for that case, in which case it would be none of the above, but I'm fairly confident in my answer. An array of 7 integers is being sorted to construct the heap sort algorithm. After the initial phase of the algorithm, constructing the heapify step, the part that we went over earlier, which of these is a possible ordering for the array, right? Rather than looking at the tree structure, they're just giving us the array, the internal array, what it looks like. But again, if you really wanted to draw it out, the way you could do that, like for problem 1, is go 85, 78, 45, 51, 53, 47, 49. And again, the way we would check this out is making sure it's a valid max heap. So which of these is a possible ordering for the array? It's possible if it's a max heap. Okay, it's the same val. So you can check all of these over here, the same 7 integers, just arranged in a different order. So we're asking which of these is a max heap. That's what the question's going about. It's what it's testing you on. It just doesn't tell you it's testing on. It wants you to figure it out. So this one's not a max heap because guess what? 49 and 57. One of those should be here instead. Specifically 57. Right? So A is not correct. Okay, so not on A. Now let's look at this one. 85's children are fine. Let's look at B's children. B's children are 45 and 47. That seems fine. And 78's children are 51 and 53. So this is bigger than both its. So 49 is bigger than both its children, and 78 is bigger than both its children. Great. So that's our possible answer. D, we can just that's not a max heap. We can rule it out. C, 85 bigger than both its children. 78 is bigger than both its children. 49 is smaller than both its children over here. He's out. E, 85 is bigger than both its children. 51 is smaller than one of its children, so it's out. So our answer was definitely B because that was the only one we have. I like to go, even though I find the right answer in multiple choice, I like to go through all the other ones if I can, if it's quick enough, because, I'm human, I can make mistakes. So this is very similar to the question I gave you on exam 2. In fact, I totally riffed on this question for exam 2 because, as Tom Layer said, which you should check out the song, which is Libochevsky, which I cannot pronounce, but Tom Layer's Libochevsky song, which is fantastic. Which is a fantastic song about plagiarism. Only be sure always to be calling it research, as he says. So regardless, which of the following input sequences will not produce this binary tree? So we're going to add these numbers in one at a time. And we're going to see, and we're going to make sure that it draws for each of these, that it draws a tree. All of them start with 5. That's good. So let's go ahead and do 3. So sorry, A, 5, 3, 4, 9, 12, 7, 8, 6, 20. What I'm looking for is for a gap to be created, essentially, for something to be, when I insert it to something, I want it to be the child of what it's supposed to be in the tree. 5, 9, 3, 7, 6, 8, 4, 12, 20. Okay. 5, 7. Sorry, 5. So sorry, we're on C. 5, 9, 7, 8, 6, 12, 20, 3, 4. 5, 9, 7, 3, 8, 12, 6, 4, 20. So let's see what happens with E, which I'm pretty sure was the correct answer here. 5, 9, 3, 6. So adding 6, 6 would go over here, which would change the entire way the tree looks. Okay. Answer 3 of the 4 questions in the space provided. Now here's where we get into things where we're like, oh, okay, so I understand what we covered in this class versus what we didn't cover in this class. Like trees, here they talk about 2, 3 trees, and just because of time, I don't go over the binary, of the self-balancing trees, or didn't have time. And I always think of, okay, maybe next semester I'm going to cover it, but there's just always so much to cover. So anyway, trees over here. We've got the keys on middle row of the keyboard, inserted into succession and initially empty binary search tree. Draw the tree after a sequence of insertions have been made, and then it says for the next problem, do it in 2, 3 tree. We didn't know, obviously, we didn't go over the 2, 3 tree in class, so you just skip that problem on the practice exam. Okay, and this is actually a great example, just like the quick brown fox jumps over the lazy dog in terms of creating a unbalanced tree, because again, this is a binary search tree, so we input stuff in alphabetical order. So S comes after A, D comes after A, but before S, F comes after A, before S, after D. Don't feel bad if you have to sing the alphabet song in your head. You have G, H, J, and you get the idea. It just keeps going to the right after this. This is an extremely unbalanced tree, which makes it great for the next question, which is a 2, 3 tree. Okay, which is one of those self-balancing trees, but it also has that case where you can have 2 nodes in an item. So 2 nodes in a now here we go. This is a question that you definitely should study. Okay, given an initial, here you are given an empty hash table of size 7 that uses open addressing. The following sequence of keys is to be inserted into the hash table: 15, 17, 8, 23, 3, and 5. Insert these keys using each of the following approaches. If an overflow occurs, says so, and indicate the element that causes the overflow. Overflow here being a collision, right? If we have a collision, show me how to do that. And then here, so all these we want to take the key, give the key X, and we want to put it in index X mod 7. Okay, so easy enough to figure that out. Not a hard one. This is again a poorly chosen one, but not poorly as chosen as key goes to 0. How do we resolve collisions? Linear probing here, quadratic probing here. Here, this says use double hashing, which basically is one we didn't go over, which simply says, but as you can imagine, you've got an HX and you've got H2X. So go figure, if this one doesn't work, try using this one instead. Make sense? Okay. So, but we'll do the 2 ones that are relevant to us. So let's see, let's zoom out so we can see everything. And zoom in. Okay. So 15 mod 7 is 1. Okay. Why? Because 15 divided by 7 it gives us a quotient, but the remainder would be 1. Be 2, remainder 1. So 15 will go into here because there's nothing in its way. 17 mod 7 is, well, it would be the 15 mod 7 plus 2, essentially, because, so, or another way to do this is just simply keep, if you're stuck on this, 17 minus 7 gives you 10, 10 minus 7 gives you 3, 3 is smaller than 7, so we're done. So again, what we're trying to do is just focus on the remainder. Hopefully you can do modular arithmetic at this point. If not, your calculator has, you've got a calculator on your computer to double check. So this 17 should go into index 3. Okay. 8 goes into index 8 mod 7 is 1, so 8 should go into here, except it can't, so it's going to go into here instead. Right? Linear probing says look for the next available space. And what if we get to the end of the array? Well, then you just wrap back around. Okay, that's what the next available space is. 23. So 23, well, 21 is divisible by 7. So 22, 23. So 23 wants to go into here, but it can't. It wants to go into, so we look for the next available space. Can't go into here, look for the next space. We can put it in, so we put 23 over here. Again, indicating where it occurs, that's kind of abstract in terms of this question. So don't panic about how to indicate it on the exam. Okay. If you were asked, I'd give you very specific instructions on how to do that. 3 mod 7, that means that 3 should try to go into here, it can't, tries to go into here, it can't, 3 goes into here, and then 5, we want to try to put 5 into here, but we can't, so we put it into here. Okay. The way again it works is that basically it's always target plus I indexes away. So we look 1 away, then we look 2 away from our initial spot, then we look 3 away, then we look 4 away from our initial spot, and 5 away. Right? And that's from our initial spot, which is going to be useful for quadratic probing because that says target plus I squared. Target plus I squared. So we look 1 away from our initial spot, then we look 4 away from our initial spot, then we look 9 away from our initial spot. Again, the trade-off here is that while quadratic probing, that reduces clumping, that reduces the number, how stuck together things are going to be in a large hash table. You do have that additional calculation of a multiplication operation, which can matter in some circumstances. Okay, so draw. Okay, same deal though, it's same mod 7, so 15 goes here, 17 goes here, 8 mod 7. So 8 wants to go into here, it can't, so it looks 1 away and finds it. 23. 23 mod 7 is, again, trying to put it into index 2. 22 tries to go here. So 23 tries to go here in index 2, but it can't, so it looks 1 away from our initial spot. It can't go there, so it's going to look 4 away from the initial spot. Got it? 4 away from the initial spot, so not 4 away from this, from where we just collided, but from 4 away from our initial spot. So 1, 2, 3, 4. So over here, so 23 will go over here instead. 3. 3 says we want to put an item here. We have a collision. So we have a collision initially, so we put 3 over here. And then finally 5, we can just drop that in over here because there's no collision there. And again, I apologize for my handwriting. My handwriting is terrible. I have done everything humanly possible to make sure that my handwriting is what it is. That actually sounds like I've made it intentionally bad, so scratch that. But actually, I've done everything I can to do to make my handwriting be tolerable, but I on a vertical screen, it's just even the little bit of help I've got with this, yeah. Because 3 mod 7 is 3. So it just tries index 3. So that's why it's trying to go there. Yeah, we'll skip the double hashing. There's no need for that. And we're going to start out by doing our graph algorithm. Let's see. Yeah, we'll continue by doing our graph algorithms here, and then we'll get into some of the coding stuff next lecture because they do have some coding problems. And again, the exam is half theory, half coding. Next lecture, of course, would be Monday. Okay, so with regard to this, notice over here it says prims and minimum MST. and minimal spanning tree, that's all stuff that we teach in algorithms, minimum spanning trees and the like. Okay, and Prim's algorithm. But sometimes, again, that gets pushed into this class, depending on which school you go to. Again, it's all spread out. For instance, generics, I taught generics because I think that's a valuable tool. It just depends on the professors and how it gets spread out. Where there's no, anywhere where we say a course ends is a very arbitrary point. So graph algorithms. I always hated these particular graphs, but hey, perform a depth first traversal of the graph shown above, starting with vertex C. Okay. Select the smallest edge first when appropriate. So in other words, if I have a choice of where to go, I'm going to break that tie using the smallest edge. Okay. In the space below, list the vertices in which the order they are visited. Right. Remember, for depth first search, you've got your visited order, and then you've got your finished order, which is when you pop out through them. Okay. So I'll circle the nodes as I've kind of identified them, or as I've traveled to them. So we start at C. Great. And so C can go to one of three neighbors. It can go to B, E, or F, right? Which one is it going to go to? The one with the smallest edge. We're breaking our ties with the smallest edge. So we'll go to B next. B says similar. I've got 4 neighbors, but the one with the smallest edge, C, is one I've already seen, right? We don't visit places that we've already been to before. In other words, ignore everything that's been circled so far. So we're at B. So we have a couple other places we can go. We can go to F, 18, E20, A13, and D17. So traveling to A is the least expensive option. We'll take that, because again, we're breaking ties with the shortest path. Okay. So now we're at A. A has only one neighbor that I haven't visited, which is D. D has no neighbors I haven't visited, so I X that out. I'm done with it. Then we're back to A now. And yes, normally you'd want to be keeping track of this in a stack, but we have so few nodes here that we can kind of mentally remember how we got to places. A, then we backtrack to B. B has 2 nodes it hasn't visited. It's got F and E, right? F has the shortest thing, so we travel to F. F has no places to visit else, so we're done there. We go back to B. B has only one place to visit, which is E. E has no places to visit. B has no places to visit. C has no places to visit. If we had an edge over here that was 50 or something, at that point we'd travel out from there. Okay. So C bad. Okay. Breadth first search this time around. Again, we are going to break ties using the this. So here I will actually set up a queue of things I'm going to visit. So I have neighbors. So C, I'm visiting first for breadth first search. And let's put my neighbors into a queue. I've got, and we're going to, and again, we're breaking our ties based off of, how far away, which is 5, 22, and 30. So we'll do B in the queue first, then E, then F, right? So we visit B next. And we look at B's neighbors. E and F are already in the queue. A and D aren't. So A should get added next into the queue. And then D should get added into the queue. And honestly, then everything's been added to the queue. We would just process the queue in order. So it would be C, B, E, F, A, D. CB fad. Okay. Dijkstra's is the more interesting one. See what I mean? Always Dijkstra's. If you don't learn Dijkstra's, it's always going to be on the exam. Always, always, always. Okay. So Dijkstra's algorithm says, let's find the shortest path starting from D at this point. Okay. List in the order which they become known, all vertices with the shortest path. And we're just going to create the Dijkstra's path for this. Okay. We're just going to create the table. for this, which is what we care about. What do I mean by the table? Well, the table is as follows for Dijkstra's, right? The Dijkstra's algorithm always has an accompanying table, which is as follows, which is, the node, the distance, dist, and the predecessor. A, B, C, D, E, F. All right, we're going to be starting at D. Its distance to itself is 0, and its predecessor is bleh. Doesn't matter. Everybody else, I'm going to say that it takes infinite amount of distance. I initialize this by saying that it takes infinite amount of distance to get to this. If you're unsure of how to do Dijkstra's algorithm, review the videos. I go through in great detail this. I'm going to assume you watch the videos on Dijkstra's algorithm. If you haven't, this is like one of the most famous algorithms. And honestly, once you learn it, the hardest part of Dijkstra's algorithm is spellings. Okay, it's not a very hard algorithm, but it is once you've learned the steps. So here we go. Everything has the predecessor of D. And this is not going to be the only time I go over Dijkstra's. The other exams have Dijkstra's algorithm on them too, because of course they do. Okay. So what we go over here is that we're starting at D. D has two neighbors, A and B. And so we now add the knowledge we gain from the node from this and see if those are better paths. So we can get to A with a cost of 10. Is that better than the cost we have to A right now? Yes, it is. It's better than the cost of infinity. So we're going to be able to say we get to A from 10, A from D to A using a cost of 10. Same for B. 17 is certainly better than infinity. Again, cost there. So we're done with D. So now we're kind of done with our initial thing. Now we look for, so we're done here. Now we look for the next node that we haven't done that has the lowest distance. That's how we select which node we're going to choose next. We look at the distance and we choose the one that has the lowest that we haven't done already. We're going to choose A. I'll mark it off since we're doing it now. A has one new edge that we haven't looked at, which is 13, A to B using 13. Does 13 have a cheaper cost? Does 10, the cost to get to A, plus 13, which is the cost to get to B, is that a cheaper cost? 23 is not a cheaper cost than 17, so we don't update our graph. Okay, that makes sense, right? We're not going to go from, if we're trying to use the shortest path, we're not going to go D to A to B. We're going to go D to B because that's cheaper. Right, if this was 50, we would choose D to A to B. Okay, so we're done with that. Next, we choose B. Honestly, I don't like this graph for Dijkstra's. It's not particularly interesting for Dijkstra's. B has to get to B has a cost of 17. So B to C, what's the cost of B to C? It's currently infinity, but we now have a better path, which is the cost of getting to B plus this new edge, which is 5. So 17 plus 5, which is 22. B. I'm going fast because again we're running low on time. Then again we have edges to E and F. And those are for infinity. So now there's 17 plus 18, which is 35 to get to F. And 17 plus 20, which is 37. Okay, there we go. 37 is, so now we've done all those, A, B, and so actually we hadn't done C yet. So C, looking at C, the only paths we get are 32, 22, and 30, which don't add anything good, right? Adding 30 to 22 would give us something in the 50s. Adding 22 to 22 would give us something in the 40s. So no. And then if we look at F, go to F next. Yeah, there isn't a better route to F from, to C from F, so we're not going to do that. And the same from E. Honestly, again, this is not a great one because we don't have to go through a lot of the edge cases, but yeah. So on Monday, what I'll do is I will finish this up. Specifically, what we're going to do is we're going to go over this problem, which I highly recommend you take a look at it yourself. This is one of my favorite problems. We actually gave, so wait, hold on. This is good information for y'all before you get out of here. This problem was on one of our finals back in 2018. Okay. So good to know this is a kind of problem we might want to ask. Again, it's a recursive problem, which means that once you write a solution, it's fairly short. Okay, so this is a good one. Okay, so that's definitely one you want to try. Then, of course, my classic way of asking, how did you do big O notation, which is give me the big O notation of what you just wrote. For this second exam, if you want to, again, take a look at this kind of stuff, skip problem 1, look at problem 2, insertion sort versus merge sort. Problem 3 and 4 might be a bit tricky, but problem 5 is really good based on the discussions we've been having previously. Problem 6 would be fine. Problem 8 is definitely a more mathematical version of heaps. Same with problem 7. These graph problems are again interesting to look at. But I'm trying to go over the ones. This question 2 over here is a heck of a lot like the questions I ask at the beginning of exam 2, right? Which is the best data structure questions. So definitely good practice for our exam here. Asking you to write another tree function, asking you to write breadth first search for a tree. Good question over here. Asking you to do Dijkstra's. And then big O questions about graphs, big questions about sorting, why we might want to use this. And then another sorting question, which I generally skip over, but these are generally good questions. Okay. So go through these. I'm not going to go through them all, but take a look at the ones I pointed out if you want to get some additional practice before we go over this on Monday.